Number 8. We're going to graph the quadrilateral RSTU, quadrilateral, just a four-sided figure, with vertices R31, S51, T5, -3, and U2, -1. I'm going to graph it and its image after a 270 degrees counterclockwise rotation about the origin. So again, I will graph the vertices first. 3, 1, 5, 1, 5, -3. And this last one, 2, -1. So there's R, S, T, U. And we're going to rotate it 270 degrees counterclockwise about the origin. So I'm going to do the same thing I did in number 7. I'm going to use my coordinate rules to figure this out. So R is at 3, 1, and R prime would be, when we rotate up 270 degrees about the origin, we switch the values of the coordinates and make the second coordinate a different sign, or the opposite sign. So this would be 1, -3. Same thing for S is at 5, 1. So S prime would be at 1, -5. T is at 5, -3. So T prime is at -3, -5. And then lastly, U is at 2, -1. So U prime is at -1, -2. So again, the rule for rotating 270 degrees about the origin is that you switch the coordinates and you make the second one the opposite sign. Again, when we talk about opposite signs, it doesn't mean you're just making it negative. If it started positive, it becomes negative. If it started negative, it becomes positive. Okay, so be aware of that. So for each of these, I just use the rule, switch the coordinates, and make the second one the opposite sign. So now I can graph each of those. R prime's at 1, -3. 1, -5. It's R prime, S prime. T prime's at -3, -5. T prime, and U prime is at -1, -2. And so there is our rotated figure 270 degrees. And so what it's done, it's rotated 270 degrees counterclockwise. So it goes here, and then, no, well, I guess it would go up here, and then down here, okay, as it rotates about the origin.
Lastly, let's talk about the idea of rotational symmetry. This concerns the appearance of a figure when it's rotated. You might think of a standard four-bladed fan. When you rotate the blades of that fan either 90 or 180 degrees in either direction, you'll notice that the figure stays the same. It looks the same as it did. This is because it has rotational symmetry. Let's look at a more specific definition and some other examples.
A figure in the plane has rotational symmetry when the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. This point is called the center of symmetry. So remember, in the past, with reflection, we talked about a line of symmetry where it's kind of like cutting it in half, and then we fold it on top of itself. That would be there. or that has alignment symmetry. With the center of symmetry, it's if we rotate it and it stays the same. Okay, right? If we rotate it 180 degrees or less, at some point, if we can get to where it rotates to be mapped onto itself to where it looks the exact same, then we say that has rotational symmetry, and it rotates about the center of symmetry. So if we look at each of these examples here, 10, 11, and 12. Okay, with this parallelogram, and you can tell rotational symmetry if I draw lines from each of the corners. Okay. So this point here would be my center of symmetry, because if I rotate this figure here, if I rotate it 90 degrees, then the points are up here, right? The points are up here and here. It kind of looks like this. I don't know if I can draw it super well. It would kind of look like that. But then if I rotate it one more time, rotate it 180 degrees, then it would map back onto itself. Okay? Because it looks the same over here as it does over here, and so if I switch them around, right, if I rotate 180 degrees, it would map onto itself. And so we would say that figure does have rotational symmetry. Okay? So yes, it does. It does have rotational symmetry, and we say when it rotates 180 degrees, okay, it maps onto itself. 180 degree rotation maps onto itself. So you can kind of see from those lines, as it's moving, is it going to map onto itself, and at what point will it? Okay. So if we look at number 11 here, same thing. If we draw lines, straight lines in their corners, we can see that there's this center of rotation right here. And if I look at this part here and I rotate it, if I start rotating it, is it going to change at all, right? Is it going to map onto itself? And it does. So if I start right here and I rotate just this, okay, that would be just 45 degrees, right? Because here would be a full 90 degrees, okay? A full 90 degrees here. And so if I just, turned everything here 45 degrees, if you imagine, can kind of imagine in your mind's eye, like just turning this octagon 45 degrees to here, it would look the exact same, right? Because it looks the same all the way around. And so at 45 degrees, we have rotation. And then if I do it again, okay, from here and then to here, it would still be the same, right? And then to here and to here as well. Okay. That would be, so at all of those points, 45 degrees, 90 degrees, another 45 degrees, 135 degrees, and then full 180, okay, it would completely map onto itself. And so it has that rotational symmetry at any point, because as I turn that, it's kind of like, you can kind of like imagine turning a circle, right? It's the same no matter how you turn it, like it still looks like a circle. So an octagon is very similar in that way. Why would we not go past 180? Well, if you go past 180, you're basically doing the same thing that you were, because you can turn it this way or this way. So in either way, it's going to give you the same rotational symmetry. And so it doesn't need to be any more than 180. Last one, number 12, the isosceles trapezoid. So if I look at these triangles again inside by connecting, okay, is this point a center of symmetry? Okay? As I move this or rotate this figure, is it going to map onto itself? Well, if I rotate it 90 degrees, okay, that would look like this, roughly. Okay? And is that on top of itself? No. And if I rotate a full 180 to where this is now down here, okay, it would look like this. Okay? And is that going to map onto itself? No, it's not. Okay? So no matter what point, 90, 180, or anything in between there, it's not going to map onto itself, because we can see that there's no symmetry in the sides. Like, you can see very clearly that this side is very different from this side, and so as it moves around, these are not going to be able to map on top of each other. So we would say that this has no rotational symmetry.
If you're starting to feel you're kind of stuck in the mud of all these transformations, I want you to remember that geometry is about gaining a visual and spatial understanding of our world. It helps us give language to what we're seeing and helps us better understand what we're seeing. And transformations specifically are giving us language for describing how figures and shapes move and change. It's because we want to look at something that's being rotated and use more advanced language than just it's spun around. We want to find a better way to describe what we're seeing, a more mathematical, logical understanding of it. In the next video, we'll continue to look at rotations and transformation compositions that involve rotations.